Hello everyone, welcome to today's lecture. Today we are going to talk about the one-way ANOVA or one-way analysis of variance. Okay, so before starting, like the previous sessions, already the syntax file is uploaded to the D2L. So make sure to run it on your side, modify the code based on your different address and library name. And also again for keeping this video short, so I already ran the codes and I'm just gonna share with you the results and the tables. So make sure also again run the syntax on your side and see the results based on the syntax that you are going to run. So one more time, let's have a quick review on the previous sessions that we talked about the different type of tests in order to find the difference between, for example, two groups. We talk about the t-test, we talk about the chi-square test based on the numerical and categorical factor variable that we had. And we mentioned that if we have more than two groups, so if let's imagine we are gonna compare three or more than three different group. We want to compare the population means between these two group or whatever factor mean between these two group. We have to use the ANOVA. So analysis of variance, which we are focusing on the one-way ANOVA. We will talk about the MANOVA as well, but technically in this course we are focusing on the ANOVA. So technically ANOVA is the extension of the independent sample t-test. So why we call it one-way ANOVA? Because it has just one factor. So the factor variable is the categorical variable that being used to define the groups. For example, we can have k different groups based on the number of groups that we are going to run the ANOVA. And the response variable is the variable that we are comparing. As an example, for example, we can do the comparison for the gender, race, political party, color, etc. The example that we can mention here that imagine you are running the one-way ANOVA, the independent variable that we are gonna use it is the categorical factor. For example, let's say it's the type of diet. So we have more than two groups. We have low carb group, low fat group, and Mediterranean group. So that's the different type of diet. So as we can see, we have three different group, and we are going to uh, predict the dependent variable, which is the numerical variable, which here is the weight loss group. Okay, so technically we are gonna see how these three different type of diets, these three different groups can be different in order to calculating the weight loss. Okay, so we are gonna compare these three groups, and in order to compare, we have to run the ANOVA, one-way ANOVA test again, because we would like to see is there any significant difference between these three groups or not. So that's how we can run the one-way ANOVA. Again, we are just focusing on ANOVA, but we also have MANOVA, which is the related if we have more than one factor, okay? And also you can have more than one dependent variable as well. For example, let's consider a study when a researcher wants to check the effect of both exercise type and diet type on two health outcomes. So right now, beside diet type, we also focusing on the exercise type as well. So right now we have two factors, two independent variables, and also we would like to see the weight loss and reduction in cholesterol. So that's also another dependent variable. So we can see that the independent variables or factors, which is the categorical variable, is the exercise type and diet type. And also dependent variable, which is the numerical variable, is the weight loss and reduction in cholesterol. So, but again, we are focusing on ANOVA in our lecture today. So like the t-test, chi-square test, we should make sure that some assumption and conditions are already met. So first of all, we should make sure that the data are randomly sampled. So that's one of the most important condition. The second one, the variances of each sample are assumed equal. Okay, so we have to test it with the Levin's test. We will see at the end of the session how we can run the Levin's test and how we can interpret the Levin's test. And also, like the previous different test, we should make sure that the dependent variable for each group are normally distributed. So that's also an important test. So we have to check the skewness and the kurtosis in order to understand that the data is normally distributed or not, which we already know how to do it. So regarding the hypothesis section, so the null hypothesis here is that all the means are equal. Okay, so mu1 equal to mu2 equal to mu3 equal to whatever mu that we have. So that's the important part that we should make sure to check as a null hypothesis. And then for the alternative hypothesis, we would like to see if there is at least one of the mean is different between these groups. Okay, so one more time, the null hypothesis, all the means are equal, but the alternative one, we would like to see if at least one of the means is different. Let's see as an example. So for example, we have the static classroom, and it's divided already in three different rows, front and middle and back rows. So the instructor understood that the further the students the further the student were from him, the more likely they were to miss class or use an instant messenger during class. So he wanted to see if the students further away did worse on the exam. So in this case,
Playing
so
from Lookup 61475.
sorry, that was my Alexa that talked. Okay, so right now, in order to understand the difference between these two groups, since we have more than two groups, we have to run the ANOVA test. But one thing that we should know that the ANOVA doesn't test that one mean is less than another or whether they are equal or something like that. It's just check that if there's any difference between these two group or not. Okay. So then later we will see that in order to understand which group are different, for example, we have to run the two keys test that we will see by end of a test. So one more time, the ANOVA doesn't tell which one is less than another or which one is greater than another. It just tell us that are they different or are they equal? And then again, we have to run some test later, which we call it two keys test. We will see on the syntax on the SAS, and those will tell us that, for example, students in the front are different from the student in the back rows, for example, just. So we will see in the example that we are going to run. So in this case, a random sample of the students in each row was taken already, and we can see that the score for those students on the second exam was recorded. So the front group, the middle group, and the back group. So this is just a summary statistics for the grade. So we can see that for the front group, we have seven different students. For the middle one, 9, and for the back, 8, and the mean average, the standard deviation, and also the variance, as we can see, already calculated. And we know that the standard deviation to the power of 2 is equal to the variance. So for example, 10.95 to the power of 2 is the 119.86. So in order to calculate the variation in ANOVA, we have to know the sum of squares. So variation is the sum of squares of the deviations between the value and the mean of the value. So sum of a square, which abbreviated as a SS, we can have it in two different versions, between groups and within the groups. So that's how we can calculate the sum of a square. And again, as we already discussed, this is not a statistic class, so you're not going to calculate the sum of squares on the between and the within group by hand. The only things that you will receive is the output of the SAS records. So then it is important for you to just how to interpret the reports, okay? But we are just going to go through the calculation also very quick in order to at least you to see it at least once in this class, in this course. So there are two questions that we should answer. First, all of the sample means identical? So for sure the answer is no. So there is some variation between the groups, as we can also see that the means are different here, 75, 67, 53. And this is what we call it as it between group variation. So we have three different groups. So between group variation, uh, which it happens because of the different factors. So we show it with the SSB, which is the sum of squares variation between the groups. And the other question is, are each of the values within each group identical? So answer again is no, because there is some variation within the group as well. This is what we call it as a within group variation. So that's called because of the error variation that we have within the group, not between the group, within the group. And we call it as a SSW, or sum of a square variation within the groups. So there are technically two sources of variation. The variation between the groups, which is because of the, again, due to the factor, and the variation within the group, which again, because of the error variation and cannot be explained by the factor. So it just happened because of the error variation. So that's the type of table that you will see as the output of the SAS. Okay, so this is the basic one-way ANOVA table, which let me bring my. So as we see here, the source of variation is between the groups and within the groups, which is the error, and the between group is because of the factor. So sum of the square for the between group, the formula is here and is related to the uh, y bar, which is the average, minus the y for the each group. So again, that's the statistical formula that you're not going to calculate it by hand for sure. So again, just in order to understand the output, we are seeing this table. And also the degree of freedom for each for the between the group is the k minus 1. K is the number of group. For example, if we have three groups, so degree of freedom for the between group is 2. And if the uh, total number of the observation, which is the capital N, let's say we have 9 in a group 1, 8 in group 2, and 8 in group 3. So in total, 8 plus 8 plus 9, which is gonna be 25, is the total number. So 25 minus 3, which is the number of groups, is gonna be 22. That's a degree of freedom. And for the total, the degree of freedom of total is the capital N minus 1, which is whole observations minus 1. And then the mean square, that the one that we should calculate also, which again the software will calculate for us, is gonna be the sum of a square between group divided by degree of freedom, and uh, mean square for the within group is gonna be a sum of a square of the within group divided by the degree of freedom. So this one is gonna be SS divided by this degree of freedom. This one, this SS divided by degree of freedom. And then we will have the F statistics. So F statistics, that's the test that we should have in order to see that if there's any difference between these two groups. So that F is gonna be a between group divided by the within group. Okay, so that's the difference between these two groups that we have. So let's go a little further. So all the explanation that I mentioned, for example, here again, the F statistics is the ratio between the mean square of the between to the mean squares of the within. So the larger F suggests a significant difference between the group means. So all the between groups, degree of freedom, and means of a square, all the explanation is here for you. So you can also read it, which I already explained all of them. So in order to run the one-way ANOVA, this is all the, again, statistical formula. I'm just repeating once for you. So you don't need to exactly do all these. Again, the only thing that matters for you is to how to interpret the output. But you need to, I mean, in the one-way ANOVA, we need to calculate the grand mean, which is the average of all the values when the factor is ignored. So, and it is also a weighted average. So, for example, the number of observation in the group one times by the average of the observation in group one plus number of observation in group two times the average of observation in group two divided by the number of observations, summation of number of observations. So here, for example, 7, the group one, times the average plus 9 times the average, 8 times the average divided by total. So the grand mean is 65.08. So then that's the formula for the between group. So between group variation is the variation between of each sample mean and the grand mean. So we already calculated the grand mean here, 65.08. And we can see that 65.08 is here. So the average minus 65.08 times by the number of observation, that's the standard sum of error between the group. And then for the within the group, the formula that we have is related to the times the variation, the variance to the power of 2 on times to the degree of freedom. So we can see here that, for example, that 310, 119, and 80 comes from this table that we had. You see the variance. I mentioned that a standard deviation to the power of 2 is the variance. So S to the power of 2, 17.63 to the power of 2 is the third 31090. So we have these three number in this analysis times by the degree of freedom. 7 minus 1, 9 minus 1, and 8 minus 1. And that's the within group. So we can see that the sum of a square for the between, within is calculated, and total is the summation of these two. And degree of freedom, again, we have three groups. Minus 1 is gonna be 2. And for the other one, we have for the within group, we have the 7 plus 9 plus 8, the number of observation minus the k, which is the number of group, which is going to be 21. And the total is 24 minus 1. So the degree of freedom is already also calculated. Again, all these are going to calculated by the software. And for the mean of a square, as we have in the formula, so it's gonna be the standard, the sum of a square divided by the degree of freedom. So here 1902 divided by 2, 3386 divided by 21. And for the total, 5288 divided by 23. So these are the sum of squares, okay? So these are already calculated. And for the F, we know that we should divide it 951 divided by 161. So between the ratio between and the within. So 5.9 is the F value for it. And then if we want to calculate the p-value for the f, we should go to the sorry, to the F table test, which again, we are not going to do that, but just very quick mention that F test is the right tail test. So you have to go to the table and see the F for the degree of freedom 2 and 25 in this case, which is gonna be 0.09 as the p-value for it. Again, the software is gonna give it to you. So the p-value is 0.009. Okay. So we already know that if the p-value we mentioned in the previous session, if the p-value is less than 0.055%. Okay, so in this case, we can reject the null hypothesis. The null hypothesis here is that the mean of these three groups are the same when we reject it, which means there is at least one group between these two groups, these three groups are different. So that's how we run the one-way ANOVA and how to interpret with the null hypothesis and alternative hypothesis. So we can say that there is enough evidence to support the claim that there is a difference uh, in the mean square of the front, middle, and back rows in class. Okay, one more time. The ANOVA is not going to tell us which row is different. Okay, we would need to also run some post hoc test in order to understand it. What is the test that we are gonna see is the two keys test. One more time. Two keys test, we will see how we can run it and how we can interpret it. So one more time, the ANOVA exactly doesn't tell us which groups are different. It only tells us, okay, there is a difference between these two groups or there is no difference between these two groups. So again, we said we have to run some post hoc tests. So the one that we are going to run is the two keys test that we will see, uh, uh, which is the very a good test in order to understand the which groups are different. We will see in the example. So in total, if we want to have some conclusion, so we work on the single factor or one-way factor ANOVA, and also by ANOVA we can say what's the if there is any difference between these groups or not, and then how we will see how we can run some post hoc tests in order to understand which groups are different. So uh, make sure to run all the syntax on your side. So first of all, download the uh, CSV file from the D2L. The file name is plant growth. So it has the plant weight and it has a different treatments that people are doing in order to check which one is more uh, what type of impact they have on the plant weight. So we have one control group and treatment one and treatment two. So technically we have three different groups. So we have to run the ANOVA test. So first, make sure to, again, same as always, create your library with your name and your address. And also with the proc import function, let's import the file as a database in your system. So make sure to run the formula well. And before starting, let's first run some descriptive statistics. So we know that with the proc means function from the plants file in the Hossein library, we call it plants as a data file. And we would like to class it based on the treatments, which is the control treatment one and treatment two. And the variable is the plant weight. So we can see 10 observation is available in each, and mean, standard deviation, minimum, maximum is available for us. Then we would like to see if the data is normally distributed, because we mentioned that we should check if the data is normally distributed for the dependent variable, which dependent variable here is the plant weight. Okay, so we can see that first. Let's sort it based on a treatment. Then for testing the normality, we can run the proc univariate function, the data Hossein library plants file, and by treatments, and the variable is plant weight. So after running, you will see multiple tables, but these are the main tables, ones for the control variable, ones for the treatment one, ones for the treatment two. And we can see the skewness and the kurtosis in all these three tables is less than absolute value of 2. So technically, we can say, okay, the data, the cutoff point, if you remember, we said that the cutoff point, especially for the skewness, should be less than 2. For the kurtosis, it could be even less than 10, but less than 2 is the very conservative and safe option. So in order to running ANOVA, we have two different functions on SAS. The first one is this one that you are seeing it, is the proc ANOVA, and the data is the plants in the Hossein library. The class is treatments, and then we have to come with the model statement here, which is gonna be the dependent variable equal to the independent variable. That's the formula structure. So dependent variable, which is the plant weight, equal to the independent variable, which is the categorical version, which is the treatment. And then we want to have the average and also run the Tukey's test. So Tukey's test in this one, the output is not easy to interpret. That's why we are going to see another formula in the next slide. But if you just run this uh, function, you will see this output. Okay, so that's the table that we have. The sum of a square, mean square, the F value, degree of freedom. So as we see, we can just easily understand. We have three different groups. So that's the between one, 3 minus 1, 2. And also we had in total 30 uh, observation minus the number of groups, which is 3. So 30 minus 3 is 27. And in total, we have 29, 30 minus 1. Sum of a square already calculated. And the mean square is the sum of a square divided by 2, divided by degree of freedom, which is 189. This one, 10 divided by 27, which is 0.3. And the F value is 1.89 divided by 0.38, which is a 4.89. And the p-value is 0.0154. So technically, the p-value right now is less than 0.05. Okay? So this one shows us the results are statistically significant at the 5% significant level. So technically, one more time, when the p-value is less than 0.05, we can reject the null hypothesis. Null hypothesis means there the null hypothesis here is mean it means that there is this there all the means are equal. Okay, when we reject this hypothesis, technically we are accepting alternative hypothesis. So it means that there is a significant difference in plant weight among the different treatments groups. Okay, one more time we mentioned that. ANOVA just telling us there is a significant difference. It doesn't tell us which one is different. In this case, which if you want to see which specific group differ, we need to run post hoc test, like the Tukey's test. We will see. The other formula that I was mentioning is this formula, running with the proc GLM, general linear model. So uh, proc GLM, the same format. We have to run the data, the class again treatment. The model is again dependent variable equal to the independent variable. We are going to check the means, check the average of the treatments, and then we are also running the Levine and Welch test. Okay, so if you remember, when we were talking about the assumption, we said that the data should be taken randomly, it should be sampled randomly, and also we mentioned that the data should be distributed normally, and also we mentioned that there should be an equal variance between these groups. And in order to test this variance, we have to run the Levine test. Okay, and the LS means treatments is the other syntax that you have. And this one is gonna be the PDF adjust two keys. It's gonna run the two keys test in order to understand which group are different. That's the structure that you should always run. So technically, the last two lines always the same. So here, the only thing that difference always is the based on the which class and which independent variable and dependent variable you need to put based on different data set that you have. So that's the Levin test as an output. So one more time, if you run this one, again, you will see this table like the one that we saw here in this proc ANOVA, the same number and the same interpretation. P-value is less than 0.05, so we can reject the null hypothesis, so we can accept the alternative hypothesis. So it means there is a significant difference between these two groups. But which group, we don't know. We have to take the two-piece test in order to understand. So, but let's also check the Levin's test. Levin's test checks if the variance of the dependent variable, which is plant weight here, are equal across the different level of the dependent variable. So the null hypothesis is the variance are equal. Alternative hypothesis is the variance are not equal. In this test, we would like to accept the null hypothesis, because the assumption for the analysis of variance ANOVA is to having the equal variance. So we would like to accept null hypothesis. In order to accept null hypothesis, technically we should have p-value greater than 0.05. So here p-value is 0.30, so greater than 0.05. So since the p-value is not significant, we fail to reject the null hypothesis. This means that the assumption of the equal variance is not violated, and the variance across treatment groups are roughly equal. So again, here, since we would like to have the equal variance between these two groups for the dependent variable, we are looking to see that the p-value is greater than 0.05, okay, which is the desired one for us. And then the last one, the Welch ANOVA test. The Welch ANOVA test is also is used when the assumption of the equal variance is violated. Okay, so here we can see that the F statistic test is 5.22, the p-value is 0.01. So with Welch, if the Welch is significant, it means we can reject the null hypothesis. It means there is a significant difference between the mean of the plant weight across the treatment groups. Okay. So for the, I think, third or fourth time that I'm mentioning, the ANOVA does not tell us which groups are different. It just tells us there is a difference between this group, at least one, or there is no difference. In order to understand, we should run the two keys test. Again, after running this syntax, at the end of the output, you will see this least square means adjustment for multiple comparison, two keys. Okay, so LS mean number 1, 2, 3. 1 is for the control group, 2 is for the treatment 1, 3 is for the treatment 2. We can see that the table is here. The comparison between, for example, treatment, the mean the number two and number one. Number two and number one, which is the treatment one, and the control is 0.3. That's the p-value, is greater than 0.05. So technically, we cannot reject the null hypothesis. So technically, we cannot say there is a significant difference between the control group and treatment one group. But the only thing that's significant here is between number three and number two. Number two and number three, we can see 0.01. Number three and number two, which means treatment one and treatment two. So there is a significant difference between the treatment one and treatment two. So we can see all the interpretation here, and we can see the only one is significant difference is the p-value of the 0.01, which is less than 0.05. This indicate there is a significant difference between the treatment one and treatment two. Okay, so technically the results show that the treatment two led to significantly different plant weight compared to treatment one. However, neither treatments, one or two, showed a significant show the statistical significant difference when compared to the control group. So that's the video lecture for the ANOVA uh, test that we are supposed to have for today's lecture. Make sure to run all the syntax. Make sure to see all the tables in the output. Try to understand according to the null hypothesis and alternative hypothesis, see different results, try to understand as detailed as possible, and let me know if you have any questions. Thank you so much.